Part of the research team at the Regional Projection Regional Climate Intelligence Group, or CSIRO, the Climate Science Centre, which is in Aspendale in Victoria. He'll be joining us via Zoom. His topic is a brief outline on how climate has changed globally and locally. So we're going to really bring it down to our level. How we know it has changed and why. Along the way, he'll explore the work of climate scientists from the 19th century to now. He will then switch focus to the future, starting with how we work out what sort of futures are plausible and to what extent these projections of the future are reliable. John will finish with what sort of climate and associated impacts that the Warrnambool region can expect in the future. And so Southwest is what he's focusing on. So John leads regional projections team at the CSIRO Climate and Science Centre, where he's worked since 2009. He brings a range of experience from previous roles, having been a camera operator in the Australian news media, a national park ranger in Central Australia, and a conservative ecologist managing endangered species in Queensland. John has a passion for ensuring the vital research undertaken by the climate science community is used to inform real-world.
Much. I'll try and get this presentation happening. A second. There we go. How's that? Can you see the full screen version of the slides? Hello, can you hear me?
Sorry, I was too excited about watching your presentation. I sat back down again. Yes, we can hear you.
Oh, great. Oh, well, I hope it lives up to expectations. So thanks very much. It's great. I'm very happy. What am I trying to say? Okay, I really appreciate the opportunity to speak to you today. So thanks very much. The brief for me for today was to give you some background to set the scene around the nature of the changing climate. So what I'd like to go through are these 7 things. Climate science is pretty complex stuff. So by necessity, this is going to be a pretty speedy Cook's tour of a few key concepts within the climate science space. So let's get moving. I'll start with what is climate, and try and change the slides. We all have a bit of a concept of what climate is, but from the scientific perspective, it is an incredibly complex system of interacting bits and pieces all around the planet. And we experience that, of course, as the day-to-day weather. I don't expect you to read all of what's on the screen or even necessarily to be able to make a lot of sense, but just note how many arrows there are. That sort of represents the ways in which energy moves around in the climate system, including from human activities like industry, transport, agriculture, but also the oceans, the atmosphere, and everything that goes on the land. So it's a complex bit of stuff. Now, we've all heard of the greenhouse effect as well, no doubt. But what people often don't understand is that the greenhouse effect is in fact a natural process. If it wasn't for the greenhouse effect, the planet would be too cold for us to survive. And so we're really lucky that we have this greenhouse effect. And if you're probably familiar with this, but I'll just quickly run through it just to make sure everybody's on the same page with this. So if you just focus on the left-hand part of this diagram, I'll grab the laser pointer to make it a bit easier for you to see where I'm pointing. So if you just focus on this left-hand side, the natural greenhouse effect side for now, the way it works is that solar radiation from the sun comes in, passes through the atmosphere, which is represented by this bit here, and reaches the Earth's surface. When it reaches the Earth's surface, it warms up stuff. We know that. We live this every time the sun shines. So the Earth then re-emits some of that heat, some of that energy, but it's been converted to heat. And so that then makes its way back up through the atmosphere, and a fair bit of it heads back out into space, and that's fine. But a bit of it runs into molecules like these on the right. There don't have to be many of these, but there's just enough for this energy that's heading out of the system to interact with these few molecules, and they vibrate like crazy and re-emit energy back down to the planet. So that little sort of, it's almost like it's a nicely balanced kind of process where we get just enough heat coming back so that we don't lose all of the heat that came in the first place, and it warms the planet significantly. And that's great. That's allowed life as we know it to evolve on the planet. What we're experiencing now is the so-called human enhanced greenhouse effect. So in other words, what we've done is enhance that effect. And we've done that very simply by putting more of these molecules into the atmosphere. That means when solar radiation comes in, give or take a bit, depending, but roughly the same amount gets reflected back. But a greater proportion of that is now able to bump into these molecules because there are just more of those molecules in the atmosphere. That means a greater proportion of that heat ends up coming back to Earth. And that's what's causing the slow and somewhat inexorable warming of the planet. So just to recap, greenhouse gas is a natural effect, but we've enhanced that effect, and that is what's causing the global warming that we've experienced and will continue to experience for some time. So that's all fine and dandy, but climate is this thing that controls the weather. So if you look at the weather over day after day after day, and you record the weather for 30 years, and then you've got a good handle on what's going on at that particular location, once you've got that 30 years of information, you can then start to analyze what the climate of your area is. And that's been done for a very long time, as everybody's well aware. But climate's not a static thing. We know this, we live this day to day. We understand inherently that the winter we're about to have won't necessarily be the same as the winter we had last year or the same as the winter before that. We know this, we live this experience our entire lives. So it's unsurprising when we look at things like temperature, and this is the temperature averaged for the entire state of Victoria as an annual average. And when we look at that, it's unsurprising that it goes up and down from year to year. We have hotter years, we have cooler years, and we know that that's just normal. That's fine. But I mentioned that 30-year time series of weather observations, and this gives you a bit of a representation of that. So this period, 1961 to 1990, is probably well known to many of you as the sort of what they used to call the climate normal. So this was an era that the World Meteorological Organization defined as the standard period for referencing climate. Now, you can pick other time periods, and other time periods do get used. But if we just look at that, the whole point of this is that you can then take the average of these annual temperatures, and it comes out as this red line here. So if we then start to think about, well, what does that mean? This dotted line now represents that average. So that's the 1961 to 1990 average, and you can compare each individual year to that average. And this is what you read, you know, in the paper, here on the news, when the Bureau of Meteorology says, oh, that last year was, you know, a degree hotter than average. This is what they're referring to. These long-term records give us an average, and you can compare an individual year to that, and that's fine. You can also do what's called take a running average, and this particular line here, this squiggly dark gray line, represents the average of 20 years, and you average the first 20 years, and then you move forward 1 year and you average that 20 years, and you move forward one more year and you average that 20 years, and that's what this line represents. And the reason for showing this is it makes it quite clear that there has been a gradual increase in this average temperature for Victoria over time, from well and truly in the 50s, pretty much continuously all the way up. It's not linear. You wouldn't expect it to be linear. You wouldn't expect it to be a straight line, but it's been going up and up and up. So that's a bit of a snapshot of climate. We'll come back to this graph a little bit later. But how's it changed and why? Oh, we came back to that graph straight away. It's changed because of us. And I've sort of spoken about the greenhouse effect, and that's the fundamental cause, essentially. And if we look at these up and downs, the average, the annual averages going up and down, it's very clear, as I mentioned, that there's this trend. Now, it's interesting to look back and over time at what this means for us as individuals. I can't see the room, but if I imagine there could be a few boomers in the room. I'm a boomer, kind of right at the end of the boomers. That was all kind of hunky-dory for us. Things didn't seem too bad. But the temperature's been getting warmer ever since then, and we passed through the Gen X and the millennials. And if there are any Gen Zs in the room, I'm sorry to say you've never experienced a year with below average annual temperatures for Victoria. And you might not ever, if I'm talking, of course, about that 1961 to 1990 average. So temperature's changed. It's pretty clear. And temperature is the most direct and obvious change because it's so directly connected to that increase in energy from the sun's rays that are now sort of remaining within the atmosphere. But of course, it's not only temperature that's changed. The warming, as the atmosphere warms, it affects the ability of the atmosphere to form clouds and to retain water, and it's redistributing the rainfall patterns around the world. And the general trend is that the areas that have always been wet are getting wetter, and the areas that have always been dry are getting drier. And that kind of plays out in Australia, but as you'd expect, when you try to look at the detail, there's quite a lot of variation within that. So what this map shows is the rainfall in deciles so deciles is like the every 10% of the that's kind of compared to the long-term average. And this shows that for since 1970, we've had below average rainfall in southern Australia in what is our wet season, so that April to October period. So southern Australia in general has seen a decline of around 15% since 1970. The largest decline in that data set has been May to July. And in southeast Australia, so this bit, there's been a decrease of around 10% in April to October since the late 1990s. The reason for the difference is that the decline in rainfall is more pronounced in southwest WA. That's a very consistent trend. You can see the series of annual totals here over time for southwest WA and for southeast Australia. And you can see that even though the decline isn't as well established in the southeast, it's quite clear. It's just been going for longer in the southwest. With increasing temperatures and, for us at least, declining rainfall, you would expect that to impact on things like fire weather. And that's exactly what we've seen over the last 70 years or so. Fire weather has become more extreme since the 50s. The season's starting earlier and it's lasting longer. We're also seeing, as you might remember from the Black Summer, more and larger fires. So the fires are actually bigger than they used to be and placing much greater demand on the resources that we need to keep them under control. And there's this recent research on these so-called mega fires. These are fires that burn more than 1 million hectares, and they're becoming more frequent, and they're occurring more frequently, but importantly, there's less time between the fires. It kind of sounds like another way of saying the same thing, but it's really important because ecosystems need time to recover from fire. Fire is a natural part of most Australian ecosystems, but there needs to be a certain period without fire in between to allow regeneration. And if the frequency of those, if the time between the fires is too frequent, then we have problems. So that's just a few of the changes that have been observed. How do we know that it's us? Well, we've talked about the greenhouse effect, but if we actually go back a bit, we've known about the greenhouse effect for quite a long time. But prior to about 1856, it was just really very conjectural. People were talking about, oh, maybe there was this thing, but nobody had really come up with a mechanism that would explain how it works. And this woman, Eunice Foote, an American woman, did some really elegant experiments, putting thermometers into glass jars, sealing those jars, and then pumping different gases into different jars and popping them in the sun and measuring what happened in terms of temperature change. And she found that of all the gases she tested, carbonic acid gas, which is what we call carbon dioxide, increased in heat the most. And she postulated that if we put a lot of carbon dioxide into our atmosphere, that would warm the planet. And she suggested that that could be an explanation for warmer temperatures on Earth way back when the dinosaurs were around, because that was a topic of interest at the time. So we've understood this for a long time. Others went on and developed these kinds of ideas further and deepened our understanding. We now have a very clear understanding of how that works. Now, we can look at how much greenhouse gas is in the atmosphere over time in a number of different ways. Obviously, we can measure it, and we've been doing that, for several decades. But we can even go back a million years, and we do that by drilling out ice cores from places like Greenland and Antarctica, because in the ice are trapped little bubbles of air, and those bubbles of air are filled with air from the atmosphere at the time that that particular spot was covered in snow. So in areas like Greenland and Antarctica, snow falls and then never melts. So you just get this progressive buildup of snow on top of snow on top of snow. And so gradually the deeper snow gets compressed and compressed and turns to solid ice. And then you have the little air bubbles trapped inside it. So because we know how far, the rate of accumulation of that snow and ice, we can measure how deep a sample came from. We know the age of that sample then, and then you can analyze the gas within those little tiny bubbles. And it's really elegant work, and it's given us this understanding of these cycles in this case, carbon dioxide, going up and down over very long periods of time. And these coincide with the ice ages, the so-called glacial maxima and glacial minima. And this is just tracking those ice ages. It's really nice. And then suddenly you get to this kind of period, and we'll zoom in on this period in this little part of the graph here, and you can see it pootling along at about 275 parts per million. And then suddenly it starts to zoom up, and it actually goes up incredibly fast. Okay, this is a pretty compressed time scale along here. There's 500 years between there and there. But on that scale, that's zooming up really fast. That's a like 40% increase. And it's increasing at the fastest rate that's ever been seen as far as we know. And at the moment, at least at the end of 2021, it was sitting at around 414 parts per million, which is a long way above where it's been for the previous million years. Okay, some impacts, and this is going to be fairly brief, but you'll all remember the extreme events from the Black Summer of 2019-20. This was a complex situation where we had drought and then heat wave and then the bushfires. So a sort of a triple whammy effect of what's called a compound extreme event. And we're able to look back at that event and analyze what happened in the context of what would have been expected to have happened if we hadn't warmed the climate in the way we have. And we can do that using computer models, which I'll talk about shortly. But by doing an analysis like that, the researchers who did this work have determined that the extreme fire conditions that occurred at the time the fires broke out were made 30% more likely by climate change. So we're able to now say quite clearly that if we hadn't warmed the climate the way we have done since the Industrial Revolution, then the conditions would probably have been 30% less extreme. That's pretty substantial. And the impact from that fire, as no doubt we all remember, was incredible. The smoke, just the smoke, impacted 80% of all Australians. That's Australians on the west coast. It's incredible that there was so much smoke generated that it made its way up into the atmosphere and then came down and just spread across almost the whole country. And these data come from the Bushfire Royal Commission. So there's been more work since, and so the numbers have probably gone up, if anything. But at the time, they had attributed more than 400 deaths to that smoke. So that's not direct effects of the fire, that's just from the smoke. And then in the heat wave that led up to the bushfires, hundreds of people died due to the heat wave. And of course, it was massively expensive in terms of insurance claims, not to mention the mental health consequences of events like that, which are profound and long lasting. But you can see on this time series plot, in this case, what this shows is the annual average temperature. So before we were looking at just Victoria, now this is the Australian annual average temperature, and this is the 2019-2020 summer. Sorry, I think I said this is annual. It's not. This is the summer mean temperature. So that's the 2019-2020 summer there, and this is where the sort of the longer term, the 11-year running average kind of puts us. And if we look at what we expect to happen in the future, and I'll talk a little bit more about this shortly, but this is where we're expected to go in the future, somewhere within this band. You know, by about 2040, we're expecting this average temperature to sort of fall somewhere within this range. If we just do a bit of a thumbnail sketch of what that might mean for a year like the 2019-20 bushfires, it looks pretty scary. If we had that kind of event again in this time frame, we would expect it to be maybe as hot as that, or at least as hot as that. So next time that happens, it's almost certainly going to be hotter again, potentially very much hotter. So the impacts are pretty pronounced. And the reason for pointing this out is that I don't want to depress everybody, but it is pretty depressing. But the reason for pointing it out is that, you know, we talk about Australia's warmed by 1.47 degrees since 1990, since 1900, sorry, 1910. That doesn't sound like an awful lot. Just a bit under 1.5 degrees doesn't seem like a lot. So we need to just look at what that actually means for these extremes. And you can see that these hottest years on record have just, you know, we've had record after record after record broken, you know, in the last 50 years. And that's just continuing to happen. And it's these extreme events that really have the impacts. And yeah, we unfortunately can remember that particular summer, and it was pretty awful. All right, so there's a whole range of other impacts, of course. One of the reasons for focusing on that one is that the work has been done to be able to ascribe a proportion of the cause to human activities, and it's not always that easy to do, but it was able to be done with that particular event. Okay, so that's what's happened in the past, and I said I'd talk a little bit about the future. So how do we do that? We don't just make it up. We don't just extrapolate. We don't just draw a line from the trend of what's happened in the past and assume it's going to continue in the same way in the future, because you will remember that very first slide I showed shows you how complex the climate system is. And with all of those interactions going on, it's what we call a non-linear system. You know, you have this much, a little bit of change can result in quite a lot of change in some other aspects. So it's not linear. So the way we do climate projections is by drawing on multiple lines of evidence in a thing called consilience, where we bring the results from different branches of science together in ways that are sensible. And they are things like Earth observations. We've been, you know, putting thermometers out in Stephenson's screens since, you know, the beginning of last century. recording temperature. We've had rain gauges out since the beginning of last century. In addition to that, we've got recording instruments in the oceans. We use satellites and radar to tell us what's going on. And so we have a really sophisticated data set of so-called observations around the planet. They're not evenly distributed, but they're all over the planet. We have our scientific and theoretical understanding, which I've talked a little bit about this morning. We have those long-term, the so-called paleo climate records. And we have those from the ice cores that I mentioned, but also from things like tree rings, mud core samples from bogs and swamps. And then we also use computer simulations. We can simulate the complex climate system, and taking into account all of these things, we can make sense of those results. So we draw together all of those things to do a climate change assessment. As I said, models are a key part of this process. And so how do they work? Well, if you think about that complicated diagram I showed you at the start, here's a kind of simplified version of, the landscape. There's a creek, there's some trees, there's the sun shining, and there's a rabbit eating a carrot. And if you can imagine, all of the different processes that are going on in that picture can be represented by mathematical equations. And if we can represent things by mathematical equations, we can solve those equations using computers. Because there are so many equations, we have to use some of the most powerful computers on the planet. And we do this by constructing a sort of simplified version of the Earth, a whole planet, from the atmosphere down to the depths of the ocean. And this is done by dividing the place up into kind of concentric rings, a bit like an onion, where every layer is made up of grid boxes like this, three-dimensional grid boxes. And there might be 40 layers going from the surface of the Earth up into the top of the atmosphere, and another 40 layers going from the surface down to the depths of the ocean. And in each of those boxes, we can solve all of the equations that describe what's going on in terms of the climate system. And so it does that, solves all of these mathematical equations in every one of these grid boxes, taking account of what's going on in the neighboring grid boxes as well, and solves all of those equations, and then steps forward in time, carries forward the results and does it all again. Then it steps forward in time again and again and again and again, and you end up with a time sequence of what's going on the planet. And they do a pretty damn good job, as I'll show you in a second, but it's incredibly computationally intensive. So we can do that, and we can simulate the climate using these models, and then we can tell the model what's going on with greenhouse gases in the atmosphere and see what effect that has on the results. And I'll talk about those in a little bit more detail shortly. But here's a glimpse at how well these computer models do. If I can make it work. Hopefully you can see that animation. I don't know if you've ever looked at the satellite images on the weather reports on the news, but this is the kind of thing that you see on those weather reports. Obviously, we're usually zoomed in on Australia, Australian news, but this isn't the results from the satellite or any of those things. This is the computer's version of what's going on the planet. Now, the computer has just been started up. They just turned it on and let it run with very little information about the real world, other than the mathematical equations that we know describe the way the climate system works. And after a bit of wibbly wobbly up and down for a while, eventually the model stabilizes and it starts to produce these sorts of very realistic looking systems doing exactly what they do in the real world. It's not perfect, but it's pretty darn good. All by itself, these models will start to simulate things like the El Nino Southern Oscillation, which brings us the El Nino years and the La Nina years. All by itself, it starts to simulate subtropical ridges, southern annular mode, all of the things that affect the weather in southeastern Australia. So they're pretty impressive. And that looks great. But just how good is it? It looks really impressive, but is it that good? So we check when we've got some computer simulation results. What we do is we run it for the 21st century, but we also run it for the 20th century. And so you can take the results from the 20th century and compare those with the actual observations from around the planet. So we do that. And when we do that, you can see at the top here, this is the whole planet. And this is sort of temperature averaged out for a period, which is 20 years in duration. And then you can compare that to the same data from the climate models version of that 20-year period and see how well they do. And you can see that if you sort of squint your eyes, it looks really good. If you look in a bit more detail, you can spot a few differences, but by and large, it's doing a pretty good job. You can look at the same sorts of results for rainfall, and it also does quite a good job, not as good as with temperature, because temperature is easier to model than rainfall. But they don't do a bad job. But importantly, they're not perfect, and we know that. But by doing this evaluation work, we understand where the shortcomings are and can take those into account when we develop climate change projections. So these models that I've been talking about operate at the scale of the entire globe. And those grid boxes that I showed you, they can be around about, say, 150 to 200 kilometers across. So they're quite large. But you can then take the output from one of those models and run it through another climate model that operates at a finer resolution. So here's an example of what that could look like for Victoria. And in this instance, we're just looking at how the computer model represents the surface of the land, because the surface of the land is really influential on what happens with the localized climate. You know, you get rain shadows, you get wind shifts caused by topography, things like that. So let's say this is the global climate model at 150 kilometer resolution, you can see that the whole of Victoria is only comprised of, about a dozen grid boxes. You then can take the output from the global climate model, run it through one of these high resolution models at 50 kilometers, and you can see that the land surface is starting to get a bit more detailed here. You can see that the high country is more visible, whereas over here in the global climate model, it's a bit of a smear, but it's not particularly detailed, but you can at least see some variations there. And then you can step that down again to 5 kilometers, and you have to do it in these steps like this. When you look at it at 5 kilometers, we've got quite a lot more detail, and that has the potential to give a lot more information. Doesn't always give better information. You have to check, but it has the potential to do that, and it very often does. Okay, so moving along, that's all fine. What's it all actually tell us for Barwon Southwest? Well, a few years back, we did some of that high resolution modeling for Victoria, and I'm just going to show you a snapshot of some of the results from that. We divided Victoria up into 10 regions. And so for Barwon Southwest, that's this Great South Coast and Barwon regions. And you can see what these plots show are the changes in average annual temperatures at different future time periods. So the 2030s, 2050s, the 2070s, and the 2090s. And these are the results from 6 simulations that we did using one of those high resolution models. And for comparison, we've got down here the results that you get when you look at all of the available global climate models. And for this particular data set, there are about 40 of those global climate models developed by groups around the world. These are the results if we follow what we've referred to as a medium emissions scenario. That's where there's been some greenhouse gas mitigation efforts put into place. And these are the sorts of results we can expect if we don't put any greenhouse gas mitigation measures in place. And you can see essentially that it just ends up getting quite a lot hotter if we follow those pathways. And the results on the left are for the Great South Coast, and the results on the right are for Barwon. A similar situation in both those two regions. So that's the story for temperature. No real surprise, it gets hotter. This tells you by how much. Rainfall is more complicated. And as I mentioned, it's a lot harder to to model. Our understanding of what makes rainfall rain is less complete as well. So these things combined mean that we usually get a bigger range of results from different models, and that's represented here. You can see we've got some models saying it's actually going to get wetter, but most of the models saying it's going to get drier by close to the end of the century. Similar story here. These pale blue bars represent the results from the high resolution modeling, and the green bar represents results from a large range of sources, not just global climate models. In the case of rainfall, we drew on some other results as well. So essentially, in essence, it looks like a drying climate for this part of Victoria going forward in time, but the amount of drying depends on what we do with greenhouse gas emissions. So that's the story with the annual average changes, but we've already talked about how, that's one thing, but it's the extremes that really bite. So what about changes in extremes? Well, one of the things we can do is we can look at how this plays out in a day-to-day sequence of temperatures and look at things like, well, how many days might we expect where the maximum gets above 35 degrees? So we've got a range of results for those, but in essence, say for Warrnambool, in the data set that we used, it has Warrnambool having sort of 5.8 days above 35 degrees per year in this 30-year period, 1981 to 2010. So that's an average number of days above 35 for those 30 years. If we compare that to that moderate mitigation strategy, what we called medium emissions on the previous plot, you can see that's expected to go up. This is the average from all 6 models, and this is the range from those 6 models. So some going up from 5.8 days per year above 35 to somewhere between 6.9 and 11.1. So possibly as close to doubling under that moderate mitigation scenario going forward into the 2050s era. If we follow that fossil intensive pathway, then a lot more days above 35. And on the right-hand side, we've got similar looking results, but these are for the nighttime temperatures. So nights where the minimum temperature stays above 25. And you can see that historically for these 4 locations, they're pretty rare. In Warrnambool, that's 0.1 day per year. So that's 1 day in 10 years, roughly. So not very frequent, and some increase in that projected into the future. Not massive, but still you've got a doubling or tripling in under some circumstances. So a combination of hotter days and hotter nights is pretty bad news for human health. It's also bad news for dairy cattle, but yeah. So some of those extremes. And what does it mean for fire danger? Well, essentially, as I said before, fire danger has been getting worse. We expect the sort of nasty fire weather to be a lot more common. And for, oh, I'm sorry, I've got the wrong data here. Dang it. I think for Warrnambool, it's somewhere around a 40% increase in the number of days where the bushfire danger gets extreme. I'll have to swap that out and send you the right data. Sorry about that. We can also look at sea level, and I won't dwell on this for very long, but these are the data for sea level rise for Geelong and Warrnambool. So we're looking at about a 4 millimetre per year increase in sea level. But there's this really useful sea level projection metric called sea level allowance, which gets away from having to deal with this range of numbers that you see all the time and allows you to work with just a single number. And what it represents is how much you would need to raise a piece of existing infrastructure in order for its current level of exposure to extreme levels to be maintained as constant going forward in time. So, for Warrnambool, under a moderate emissions pathway, we're looking at a 0.23 metre, so 23 centimetre rise. So if you've got a piece of infrastructure that currently gets inundated, once every 20 years and you think that's okay, then by 2050, you'll need to have made that 23 centimetres higher to maintain that level of risk exposure. All right, I'm running out of time, so I'm going to have to speed up, sorry. Why are there different results for the future? We go back, I just said, we've got this range of numbers. Why do we have to have a range of numbers? It's really annoying. Yeah, I get it. It's really annoying. The reason that we have ranges of numbers are complicated, but one of the principal ones is that we can't know how much greenhouse gas there's going to be in the atmosphere in the future. It is purely and simply unknowable. It depends on so many factors, including how the global community responds to the requirement to reduce greenhouse gas emissions. So the way around that is to say, well, what if we do this? What might that mean for the climate? So if we follow X pathway in terms of greenhouse gas emissions, we will get Y change in the climate. So you'll hear people talk about greenhouse gas emissions scenarios, and that's what they're talking about. So the whole purpose of greenhouse gas scenarios is so that we can explore how the climate will respond depending what we do in terms of reducing our greenhouse gas emissions. So they're a fundamental part of the climate change research and really very important. But one thing to keep in mind is that you'll hear people talk about greenhouse gas emissions and greenhouse gas concentrations. And you need to understand the difference because some people get these things mixed up and they might use the terms interchangeably, but they're very different things. Emissions are what we, as through our human activities, put up into the atmosphere. So the gases that we generate and release into the atmosphere, and they go up into the atmosphere and they gradually become mixed throughout the entire atmosphere. But some of those gases get absorbed, some of them get taken up by plants, some of them get absorbed by the ocean, an awful lot of them get absorbed by the ocean. And that leaves a certain concentration of those gases in the atmosphere. And it's that concentration of gas in the atmosphere that actually drives the climate change. So if you think of emissions are what are relevant in terms of things like, policy agreements and the Paris Agreement and the greenhouse gas inventories that every country on Earth does. And in concentrations are the important thing when it comes to understanding what's going to happen with the climate. The concentrations drive the climate change, and we use these what-if scenarios of future concentrations to drive the climate models to see what they might tell us in terms of future climate. And another reason why there's a range is that every time we run a simulation of the future climate, it's just one way in which that future climate could play out. So even for a given emissions pathway, different models give us different results. And even if you run the same model more than once, you'll get a different result each time you run it. And it's just the nature of climate. There's an element of chaos in the climate, so an unpredictability. And if you like, you can think about the past as just the one version of all of the possible pasts that we've experienced. We could, if we could reset the planet and run it again, we would get a different sequence of hot years and cold years than the one we've experienced. And so when we are modeling the future, we've got to try and understand all of those possible futures if we're to plan accordingly. So this is just an animation to give you an idea of how much different versions of the future could be from each other, even for a given emissions pathway. So these are the low emissions pathways, and you can see that different model outputs are giving quite different results within that, particularly in terms of the sequence of events. For high emissions, same deal. You've got this model run goes very high, another one stays quite low. So there's no getting around the fact that there will always be a range of results in climate projections. And finally, we've talked a little bit about natural variability, but just a couple of things to point out. Firstly, that there's a whole bunch of causes of climate variability, all of which are natural, and then there's the ones that are not. And so these are the ones that this is the reason we have a change in climate, and this is the reason why we need to run computer models to understand what the future looks like. Sorry, got somebody calling me. And so just to finish off, these are the sorts of causes of the natural variability that we experience in Australia. And you can see there's a range of different causes, and they all operate on different timescales. But there are some here you'll be familiar with, like El Nino, La Nina, subtropical ridge you may well have heard of. The southern annular mode is the thing that brings a lot of the rain to southern, eastern Australia and Tasmania. Blocking highs are the things that often cause heat waves because they just sit there and make the hot weather sit over the land. And east coast lows are those things that can cause so much damage, particularly on the east coast with storms. All of those things are natural, but they are all being affected by climate change. For example, this is a time series showing the global temperatures. So the average global temperature year by year from 1950 through to 2021. And sorry, people are trying to ring me. And the El Nino years are colored in orange. The La Nina years are colored in blue. You probably all remember that 2021 was the first of that 3-year run of La Nina years that we had. And you can see how they've changed over time. And what's going on? Very significantly, you can see that we've got that 2021 La Nina year, which is the occurrence of La Ninas and El Ninos are completely natural, but now that they're happening against the background of this climate change trend, you can see that this La Nina year was hotter than any El Nino year up to about 2010. So that's a pretty significant change in the climate. And I'll finish there.